Welcome back to the Bit of a Tangent podcast. I'm Gianluca, a master's candidate in artificial intelligence, and I'll be joined, as I always am, by my co-host Jared, the medical student polymath who is currently re-implementing PyTorch for fun. In this technical episode, we explore the relationships between linear mathematical functions, the laws of physics, the anatomy of human brains, and the unreasonable effectiveness of deep learning. Now, with these discussions, we think it's important to make ideas as accessible as possible. And to that end, we spend time throughout this episode doubling back to define terms or explain fundamental concepts in machine learning and mathematics. At the same time, we want our discussions to be authentic and to push the boundaries of existing thought, which sometimes means we stumble into novel concepts that we are not yet fully equipped to articulate. The result of these two ideals is a conversational roller coaster, and that's precisely what this episode is. If you aren't looking to have your intuitions challenged, then this is not the episode for you. But if you're the kind of person who gets a kick out of being exposed to new ideas and drawing connections between biology, information theory, and data science, then you're in for one hell of a ride. We start by discussing the term linearity and why it's so often used in machine learning contexts. Neither of us are professional mathematicians, but we hope that our intuitions on this topic can expose new people to these concepts in a less rigorous but still valuable way. Those of you who are mathematicians are welcome to write or tweet to us and point out anywhere we went wrong. We always appreciate it. From there, we ask how it's possible that our modern AI systems are so capable of performing remarkable feats, especially ones that seem to violate the assumptions of information theory. We spend some time discussing how neural networks operate and how convolutional networks seem to defy the laws of physics. We also touch on the universal approximation theorem, Max Tegmark's ideas about cheap learning, Markov processes, the Manifold Hypothesis, and how the human brain performs dimensionality reduction every time we string a split infinitive together. In essence, this episode explores the relationships between the physics of our universe and the performance of deep neural nets, asking why they are capable of what seems to be magic and why they happen to look so similar to the structure of our brains. We even threw in some podcast recommendations at the end. Those, and everything else we mention, can be found in the show notes of the episode, as well as on our website, podtangent.com. So, buckle up, friends, for this episode of Bit of a Tangent. I've had this idea of linearity and linear functions and what that means and how that is a separate kind of thing from other mathematical functions and has its own special properties. And people have been throwing some ideas around at work that I've been listening to and jumping in on, but I felt kind of unsettled about these ideas, and I felt that there was a lot more going on here that I hadn't dug into yet. And the context of linearity and why it's so important is especially relevant in the modern landscape where we see deep neural networks everywhere that are performing to a almost unreasonable standard and achieving things that verge on superhuman. And yet there is this assumption that they shouldn't be able to do that. In a vacuum, one might not think that that would be the case. And so I started thinking a lot more about this idea of linearity and linear functions and how that was an integral part of deep neural networks and really the fabric of the underlying reality. And I thought that would be a really interesting jumping off point for us to start going on some conversational tangents.
Yeah, I think that's great. And, it's always difficult, I think, with a hard sciences topic to know exactly where each person approaches it from, right? So, it's conceivable that some people are hearing the word function and just thinking, oh God, not again, right? And to some people, they're hearing us speak about, topics which have a very definite mathematical formalization, right? Linearity, if you really get into it, becomes very specifically defined in ways that I don't particularly understand or necessarily get into. So yeah, I think with all deference paid to the fact that neither of us are professional mathematicians, let's try and talk about maths and physics
absolutely.
and deep learning and computer science.
Exactly. Well, I think the beauty of it is that very few people are experts in all of those things. And so when you start speaking at the intersection of multiple different disciplines, you are forgiven for not being an expert in more than one of them or any of them, really. And I think, secondly, it's really great that we can have a conversation as people who have limited experience in these topics in a way that might help other people make critical steps in their understanding or give them new kinds of questions to ask, and really just expose ourselves to ways we might be thinking about things incorrectly or not fully comprehending the real scope of the topics. And so I think that it's a great challenge for us and a nice opportunity for people listening, whatever their background may be.
Yeah, that's a great point. So there was something you said there which I think is useful to clarify. And you sort of mentioned that with deep learning and deep neural nets in particular, we're starting to get superhuman results almost, right? So maybe you can outline a couple of examples of that, or maybe just what you mean. And then that's not even at the point yet where we're explaining the idea of deep learning. But let's start with just what results are we getting? Why is this even interesting to talk about?
Yeah, absolutely. So obviously the field of AI has been around for many decades now. And for many decades, there have been notable advances. You've got IBM Watson winning Jeopardy. You've got Kasparov being defeated in a game of chess. And then in more recent years, you've got the game of Go being conquered, so to speak. And that was using a deep approach. And really, the deep learning approach has only become feasible in the last 2 decades as a result of more computing power, for reasons we'll get into in a bit. And it's really just the most effective technique as the amount of data that you're working with scales. So all the other techniques might be good on smaller data, but they have diminishing returns as your data size increases. And so with the more data we have and the more computing power that we've had recently, it's possible to do things that we couldn't do before. So great examples are beating Lee Sedol at the game of Go, which happened not that many years ago. And more recently, OpenAI has been creating a Dota team. So it's a video game where you have 5 human players playing against 5 other human players. And now instead of human players, there are 5 AIs that cooperate and play against the humans and are able to win against professional players in this very complex type game. And those do involve something called reinforcement learning, but they have deep models underlying that framework. So, that's to name a few sort of major examples, but really just any time Facebook is suggesting to you that you should tag a person by identifying their face and then suggesting who the person might be, or any time you are able to search through your Google Photos library using a keyword like motorcar or beach, and it returns all the images that have that in it. That is an example of deep learning really excelling. And I think computer vision is a case where deep learning has been exceptionally effective and very tangibly so for humans, because we can instantly see that effect size.
Neural networks, and specifically ones using this deep learning technique, right, are getting to the point where they can do things that we have typically thought of as only being possible for humans, right? And they can do them as well as we can sometimes. Everyone feels that their calculator does things better than they do, right? No one is in awe of how good calculators are. But we have been previously sort of the masters of things like recognizing visual objects or, drawing, sort of like taking complex patterns and recognizing it and deriving laws. And now, suddenly, with these deep learning techniques, those things are becoming tractable to algorithms and to machines. And I think then the natural question follows, why is it that you marvel that this works at all. Like, why is this such a difficult thing to do? And why is this an interesting question to even talk about, that it works at all? Why is that surprising?
Yeah, so I think the example of a calculator is a nice one there, because if you think about a simpler version of a calculator, or let's say a non-electronic version of a calculator, you have an abacus, right? So you've got beads that are moved around to represent different quantities at different orders of magnitude. And really, an electronic calculator is a glorified version of this. You are essentially just shepherding electrons around into different positions in ways that produce the kind of consistent results that allow you to use it, much like you would an abacus, to store information, to add it, and to be able to do that in various different combinations and with various numbers of repeats, to be able to compute just about any basic arithmetic operation. And so really, a calculator is not an example of intelligence because it has no goals, it has no objective, and it has no way of improving itself over time. A calculator is simply an exploitation of the underlying physics of electrons, and using those underlying physics, much like you use the physical, tangible Newtonian physics of an abacus, to store values and add values, etc. Whereas when you look at a deep learning system, it now has a goal. It's given something called an objective function, and it tries to make itself as good at that goal as possible using a whole bunch of training data, which means it's learning and it's getting better over time. And it's not simply exploiting underlying physical laws. It's not being designed from the physical level, and it is being designed to be a good architecture for learning. And the true power of it is that through time and through enough examples of underlying data, you can produce something that you could never have created from the ground up in the first place, right? You cannot build a model that can classify faces the same way you build a calculator. You can't actually go and plan out the circuit design in a way that you can build something that advanced. It's not theoretically impossible. It would just take so many years and so many hours of work that it's totally infeasible.
Yeah. I think what's useful here maybe to explain almost what a neural net is in rough terms, right? And then why this image classification task, and I think we're going to use that as our almost canonical example. Why is that a difficult task? Why does that at first appear almost impossible? And then we'll get into why neural nets somehow managed to so-called, I think Max Tegmark called it the combinatorial swindle.
Yeah, exactly.
And so I think getting into those different things, right? So, and what a neural net, right, is it's a way to find a function, and functions take inputs and give you outputs, right? And a neural net is just the function, the very, very complex function with lots and lots of variables that takes as input an image and gives you as output a label for that image, if you were doing that kind of task, right? But, you know, when people think about these, unless they know very much what they're talking about, they're expecting something more magical than that, whereas they really are just these ways to approximate a complicated function, right?
Yeah, so I think we should probably dig into why you would want to approximate a function and how you go about doing that and why you have different kinds of functions in a bit. But just for anyone who's not familiar with the core difference between AI and machine learning and neural networks and deep learning, I think a really good mental framework to have is to just think of it's an Euler diagram, or you would call it a Venn diagram in contemporary parlor speak, shall we say. But so imagine you've got some kind of outer circle, and that is AI. And then within that, you've got another circle that is machine learning that makes up some subset of that. And then within that machine learning circle, you've got another little circle that's deep learning, right? So not all machine learning is deep learning, but all deep learning is machine learning. I think that's a good model to keep in mind, right? So there are other ways to do AI than machine learning, and there are other ways to do machine learning than deep learning. But deep learning, as we've touched on before, is just incredibly effective as your data size grows. And what deep learning is it's the use of neural networks. And neural networks are systems of interconnected nodes, or neurons. You can think of it much like a neural network in the brain, albeit a very simplified version. And you just pass information from one node to another, and you perform very simple mathematical operations on them, right? So between each node, you are performing a very simple linear function, and at the nodes, you perform an activation function. Much like neurons fire in the brain at some critical threshold, you would have an activation function in your artificial neurons that, air quotes, fires at a certain threshold. And this is a very important point that we'll come to in a bit. But the distinction between just general neural networks and deep neural networks, and therefore deep learning, is how many layers of these you have, right? So in a very simple network, you would have input, you would have one layer of these neurons, and then you would have output. But in a deep neural network, you have many of these so-called hidden layers between your input and output layers. And this is where Tegmark's combinatorial swindle comes in. This is where the real value of deep neural networks come in. And it seems, if you argue from first principles, that shouldn't be the case, right? There is definitely some woo-fuckery going on here. And our sort of journey tonight is to figure out why and how and what that means for machine learning as well as our lives in this universe. And I think from that point, it's probably wise to then get back to what we mean by the different classes of functions. And starting off, we should discuss probably linear functions.
Go for it.
Cool. So if you kind of oversimplify the standard mathematical understanding of the different kinds of functions, you get the kind of framework I'm about to present to you. And it's a really nice one because it's simple enough to keep in mind, and it will help make sense of a lot of things. It's helped me a lot. And essentially, this just is a breakdown based on some of the core groups. And it's an Euler diagram again, so you can kind of visualize this. Unfortunately, we don't have the visual aid on a podcast, but here goes. So remember that a function is just something that takes in one or more inputs and produces one or more outputs, as everyone's familiar with from high school maths. And in mathematics, you've got two major groups, right? You've got elementary functions and special functions. Now, we're not going to worry too much about special functions. They're called special functions because they're special. So examples of this would be sawtooth functions, the floor, ceiling functions, absolute value functions. These are kind of the functions that you have to specify with almost rules a lot of the time. And, they're nice to do in a computer program, but they're not so easy to write out in standard mathematical notation. So that's a good heuristic for identifying if something's a special function. But let's ignore those for now. Those aren't going to feature too heavily. The other major group is the elementary functions. So these are things that you can make up with basic mathematical operations. And within that, you've got two major groups. So within elementary functions, you've got algebraic and transcendental functions. And your algebraic functions include the polynomials and the roots. So the polynomials being like the quadratic and the cubic, and also the linear function. Linear is a subset of polynomial. So people will be quite familiar with polynomial functions from school. It's just something of the form ax squared plus bx plus c.
Right.
Right. So those kind of things. And then obviously the roots are square root, cube root, nth root, etc. And your transcendental functions are your logarithmic functions, your trigonometric functions. And so those are all your elementary functions. And so importantly, you've got linear functions are a subset of polynomials. You can think of them as a polynomial function where the degree or the power of that polynomial is going to be set to 1, right, in every case. And so it's functionally equivalent to not having the power listed there at all.
So, I mean, the simplest example would just be y equals to x, right?
Yeah, exactly.
All right. Just to keep us grounded in something less abstract here.
Yeah, so a linear function is just going to be anytime you can draw it as a straight line on a graph. That's going to be a linear function. And the final characterization that's important here is the difference between continuous and discontinuous functions. And this is crucial. If you take anything away from this whole framework, it should be polynomial functions, a subset of which are linear, and then the difference between continuous and discontinuous functions. Now, the framework that I've given you so far doesn't break things down by continuous or discontinuous, because really anything can be made discontinuous. And what we mean by continuous or discontinuous is, as many people would have learned in school, if you draw it on a graph and then you take a ruler held vertically and you move it from left to right over this picture, is there any point at which it breaks and your ruler is not actually touching the line you drew? Right? Are there sort of gaps in your function? And that would be a discontinuous function. And you can build these with piecewise functions where you just define it for some subset, some range. But a lot of functions are continuous. And in the natural world, I think it's very rare to come across a discontinuous function. And so yeah, the really important thing here is that linear is a subset of polynomial, and you can draw it with a line on a graph. And then you've got continuous versus discontinuous. And by continuous, we just mean that that line doesn't jump, it doesn't break anywhere. There's no discontinuities. And so this is a really nice framework for talking about these things, because linear, polynomial, and continuous versus discontinuous come up all the time in discussions about deep learning, neural networks, and the underlying physics and abstract mathematics.
All right. So from what you're saying there, right, I don't think many people would find it intuitive how you go from quite literally some of the simplest functions you ever see at a high school level, right? I mean, some variation of y equals x, right? You add some constants, you scale things, but it's not much more complicated than that.
Yeah, there's like the classic y equals mx plus c, right? That everyone's familiar with. I think take us away with discussing the step of how we go from linear to approximations based on linear.
Okay, so most people at least are somewhat familiar with the idea of a derivative, right? You can have quite a complicated function, and most people have at least seen that when you take the derivative, you get a tangent, right? And that tangent you can represent as a straight line that, is tangent or just touches this very complicated function that you have, right?
And if you're very confused about what we're describing, you can just look at the icon of this podcast.
There we go. A tangent. So there's this sense in which you can build any arbitrary function, right? It can be as complicated a curve as you'd like out of small but simple straight lines, right? Yeah. I mean, this is intuitive to anyone who has seen a video game or done anything digitally, right? Where we can't represent perfect curves. So we make up our curves of very, very tiny straight lines.
Absolutely.
So if you've seen like the progression of, like, let's say video game graphics from maybe the 1990s to now, well, in the 1990s, because of limitations on computing power, we could only use a few straight lines. And so characters tend to be quite jagged, right? Whereas now, because of more computing power, we can chuck more straight lines. And as you put more straight lines that are much smaller, they start to look very much like a curve, even though that curve is still made up of very small straight lines. So in some sense, if you zoom in close enough on any curved line, at some level of zoom, it becomes basically indistinguishable from a straight line for a short distance.
Yeah.
And I think that's the key idea here.
So it's this idea that a set of linear functions can approximate some other kind of function to arbitrary precision. If you just keep zooming in and adding more, it just gets closer and closer and closer to perfectly approximating it.
Exactly, right? And the amount of error gets like very, very small the more that you zoom in. And this is sort of related to the idea of the Taylor expansion for functions. This is just also
this idea that would come up in sort of your first year of university maths.
Exactly.
Taylor series, Taylor expansions, and how they can be used for approximation. So people may be familiar with that, but the core idea there, I think that's a really nice, almost example really that you've used. It's like, well, when we had limited compute, we used to use fewer lines to approximate, but as we got more, we were able to do more precise approximations because we had more resources available.
Exactly. So it is just this interesting fact that you can get very complicated functions, which you might be describing. Imagine something that started off with 5x to the 10 and then went down from there, right? And that's just a polynomial, right? But we can get much or most of what we want to know about that function using just straight lines at certain key points.
Yeah.
And the beautiful thing about straight lines, right, is because they don't curve by definition, they behave very well. And that notion of being well behaved, it sounds nebulous, right? But it's literally just the idea that you can move along that line and you're going to change very predictably. But again, going back to this idea of limitations in computing power, well, turns out if you have a straight line and you know exactly how that line changes as you move a little bit along it, well, that saves you a lot of computing power, because now instead of having to do, let's say you wanted to move a little bit on a function that had like x to the 10 plus x to the 5, right? You'd have to compute those two values, right? It's much easier if you had a straight line that connected some small region and you only have to move a little bit up the gradient of that straight line, right? So again, there's this notion in which linearity is not only a way in which you can build an arbitrarily complex function, but it also is computationally, let's say, it's computationally thrifty.
It's much closer to just addition, which is fundamentally what computers are having to reduce everything to. Like even multiplication is just repeated addition. And so the closer you are to that, the easier that reduction is, and the fewer overall computing operations have to be performed.
Yeah, exactly.
Okay.
So maybe now is an appropriate time to go back to what we were saying for why it is that if we just started naively, if we'd never seen deep learning work at all, why you could make the argument, and a convincing one at that it wouldn't work.
Well, so a nice example, I think, is actually one that the physicist and general deep thinker Max Tegmark presents, which is if you're trying to do an image classification problem, which is one of the sort of standard problems in machine learning, right? You want to take a picture and tell me if there's a cat or a dog in it. Or a cat or no cat, to be even more specific. You have an image now that's got, probably a few hundred up to 1,000 pixels on each of the edges, right? So when you talk about like a 20 megapixel image, well, you've got 20 million pixels there. And those pixels, if they're in color, they're holding 3 sets of values that are between 0 and 255. Right now, if you go and actually do the maths there and look at how many possible different images you could have, you get a number so large that it's greater than the number of particles in the universe by a long, long way. And what's interesting about this is that from a sort of first principles approach, you would have to think that, okay, if you're going to make a sort of lookup table for knowing whether there's a cat or in this image or not, you would have to, for all of those possible different states that could be achieved in these images, whether or not there's a cat in it. And so you have to create all of that. But obviously, if it takes more different options than the number of particles in the universe, well, you can't physically create this thing or store it or access it, right? So the fact that we have these computational models that can do this with not even trillions of parameters or billions of parameters, but thousands to millions, right? With incredible high levels of accuracy is really kind of counterintuitive. We've come to accept it, but it's, if you were from another universe that had similar mathematical properties, but didn't have this kind of weird quirk, you'd be completely shocked by this result. It's almost like you get all of this for free, right? And this is what Tegmark at least calls cheap learning, right? And this is one of the two things that we have in these deep neural networks that are giving us this unexpected and almost unreasonable performance that we wouldn't otherwise expect to get, right? So the other one is it's deep, right? So it's cheap and deep, right? These modern neural networks are cheap in the sense that you can get good results with very few parameters, as in the image classification example. You don't have to describe every single pixel to be able to accurately classify if there's something in the image. And deep. And this is the sense that depth makes training things much more effective, which gives us better results.
I just want to check maybe my understanding of this image problem that you laid out, right? So as you said, you've got this image And we've spoken before on the show about the idea of a space, this abstract notion of basically all of the possible ways a thing could be, right?
Yeah.
And if I understand you correctly, what you're saying is that for just one image, right, that has a couple hundred pixels on each axis, the number of different ways that that image could be is just so vast, right, that if you were relying on this algorithm, this network, to find the very tiny proportion of ways that those pixels represent a cat, right? Like, a cat can be in different colors, it can be in different orientations, but if there are more possible images than particles in the universe, then the number of ways that you can find a cat in that set is so small as a sort of percentage that you would almost never expect a function to find it, right?
Absolutely. But even the subset that are classified as cats would be impossibly large if you're having to define it by the pixel values, right? But somehow we can have just, a few thousand or a few million parameters in our network. So literally just values that get multiplied by whatever input you pass in this very linear sense. And so like a good way to think of parameter is like in that basic linear equation, y equals mx plus c, like m and c are your parameters there.
All right. Those are almost the values that you're trying to learn, and almost, I think, maybe complete your thought there. Some process of that idea of training is teaching our network to learn those parameters, to find values for m and for c. If this is a very, very simple network, and it's not this simple, but it's just this a few times over, to find values for m and c that make this function work, right? That take in an image and give out the label cat if there's a cat in that image.
Exactly. And this brings us to, the whole purpose of deep learning is the fact that you can learn from data, right? We don't start out by trying to build this function or this model. We don't build it like we build a calculator. We instead build something that is capable of updating itself using these internal parameters, and therefore we say that it's learning over time. And I think this is a good point to probably introduce the universal approximation theorem.
All right.
And this comes from mathematics, but it's relevant to machine learning, as you'll see. And it essentially is a theorem that states that a single layered neural network with a finite number of nodes in that single layer can approximate any continuous function, right? So remember, we classified all these different functions, and we said that these neural networks are using linear functions with non-polynomial activation functions, so like a sigmoid function, which is an exponential. And by sort of layering these things, we can create continuous functions. But the universal approximation theorem says that it's possible to approximate any continuous function with a finitely sized single layer neural network. Right, which seems crazy.
Well, it doesn't seem crazy if, let's say, that your experience with functions is, I get some f of x and I get f of x equals x squared. I think it helps when you say to yourself that phrase approximates any function, right? Included in that set of any function, right, is the function that can take a picture of a cat, right? Take those pixel values that represent the colors and the area where those colors are, and output the name of that image. I think part of the problem that you run into here is if people aren't familiar with, or maybe if you just don't conceptualize this whole idea of any function, literally all the other ways that a function can do something for you. It's not just, this very trivial sense that maybe, high school maths leaves you with. And that's interesting and that's exciting. And that's why this is useful, right?
Yeah. So anyone who's sort of familiar with linear algebra and vectors and matrices will be aware of the fact that you can sort of take these big tables of data. So you could think about them as spreadsheets if you're not familiar with working with matrices. And you can essentially just like add them or multiply them together, right? So you can do the equivalent of taking these many different things that have to operate in sequence, and you can just multiply or add them together and get one thing that has the same overall result, right? So I think this is referred to as a composability, right? So another way to think of this is you might have one function f and another function g, and then your model takes f of g of x. So you feed it an x, it runs it through g, then through f, and then gives you the result. Well, now you could just like compose these into a single function h that does the same thing with a single function, right? So from that sense, it does make sense that you can have just one function, that you can have just one layer that can approximate any function. But it seems once again that it's like we're able to do a bit of magic here, right? So adding on to the universal approximation theorem, because the drawback of it is that it says while this is, in principle possible, that you can do it in a finite way, it doesn't really put a bound on that finite, right? So it could just be a very big finite. And like we discussed before, if it requires all the particles in the universe, well, then it's not really practically feasible. And the other thing that it doesn't say is anything about whether it's learnable. And, the actual reading between the lines there is that is not necessarily learnable. And it's almost certain that you won't be able to train this neural network, right? So what Leshno et al. Found in 1993 was this add-on to it, which was essentially that if you have a multi-layer feed-forward neural network, so instead of just a single layer, you now have many, and as long as you have non-polynomial activation functions, which the default ones do, then you can approximate any constant function, right? So it's saying this universal approximation theorem holds for a single layer, but when you add more layers, it then becomes learnable, right? It then is possible to train this neural network in a practical sense, and yet still have that property of being able to approximate any function. And this is amazing, right? Because what it tells us is that all we need is linear operations and these non-polynomial activations, and we can approximate any function. We can essentially throw the other functions out because we can approximate them very precisely using these fundamental, simple building blocks. And instead of having the difficulty of trying to do it in one go, we can just compose them in these many deep layers and be able to do this combinatorial swindle, which feels a bit like magic.
Why is it that we can do this magic, right? So you've given us the universal approximation theorem, which is at least part of the answer. But still, even if you can approximate like an arbitrarily complicated function, this doesn't really answer Tegmark's paradox, right? At least in my mind, of that function is still going to be so complicated. Why is it that we would expect to be able to find that subset of images that represent cats, right, in the space of all images, which can be shown to be larger than the state of the universe in some sense?
Yeah. So, we have the deep aspect to some extent here, but the cheap aspect of why we need so few parameters to still be able to get such accurate results seems like a mystery. Right, but it's at this point that we start going, okay, but what data are we throwing into these things? Right, like you're not throwing in random noise. You're throwing in pictures, and pictures come from cameras that have captured beams or photons of light, and these photons have bounced off objects in the real physical world, and everything here is following physical laws.
All right, yeah, I'm following you there.
And so these images that are coming in aren't generally in human applications that we use them for, aren't just, random information. They are very much a reflection of the physical world. And so it's actually a much smaller set of things that are coming in. And the physical world is very easily modeled by a few quite simple mathematical formulations.
All right.
And this is what we mean when we say the laws of physics, right? So people are familiar with something like Newton's laws, right? And so like a nice one to use is F equals ma, that everyone would have probably learned at some point in school if they had any kind of science background, right? Which is force is equal to mass times acceleration.
All right.
Right now you've got in this very simple linear equation, a very powerful law of the physical world, right? And the idea that these kinds of well-defined low parameter equations describe most of the things that happen in the physical world seems to follow through in our networks. We have to ask ourselves is which way the arrow points. Does the physical world have these properties and that's what makes our networks good? Or is it the fact that our networks are in the physical world that makes them good? Or is it that we stumbled upon this somehow and it just happened to be that these structures are really effective for encoding these physical laws?
So basically what you're saying is that we live in a universe, and for reasons that are, I would say, not entirely known, we just happen to live in a universe where the laws of physics are simple, in air quotes there, because, they still take a few years of studying physics, but at least relatively simple enough that they generate data, information, in a way that is predictable enough, right, that it's not like it's just random scatterings. You can almost expect to find answers or functions, in this case, that approximate this data in ways that are almost computationally tractable. And the reason we're saying that happens is because the pictures are artifacts, you could say, of the physical universe. The physical universe obeys physical laws. And so we're almost expecting the set of all images to be constrained by what is possible under those physical laws. And if those physical laws are simple enough, then suddenly that's where you're maybe getting that swindle, the cheapness you're talking about.
Exactly. That there's some kind of mirroring between the physical world and the laws it seems to obey and our representations of the information coming from that physical world. And because we have that sense of mirroring, we're able to represent ideas with much less information than you would otherwise expect.
You see, so that is just an amazing idea, right? And if anything, it kind of makes me think of how this might relate to another concept that we've spoken about before, and that's sort of the relation or not between the map and the territory, right? And, this was, as a reminder, where you can have reality, right? And we'll call that the territory. And we generally want to get some information about reality. And so we create maps, and maps of reality, well, because they are maps, right? They lose some information, but losing information isn't a big problem as long as you are taking out information that is useful and discarding redundant or possibly less useful information, right? And the next natural question to ask, and you started to get into it there, is that direction, right? Why is it that this neural network structure works, right? Why is it that in the universe with physical laws like this, we find that stringing together a bunch of nodes, which you could also call neurons, in this particular way with this activation function you mentioned, why does that follow these laws of physics? And if you follow the reasoning here, well, one answer might be, well, we don't know exactly why, but we know that it works because our brains are analogous in many important ways to these neural networks, and our brains have evolved to create maps of reality. And so it sort of follows from that if evolution found that to model reality accurately, the best way was to create nervous systems connected the ways that ours are, right? Living creatures on Earth, then mimicking those nervous systems in a computer it's now doesn't seem so outlandish that kind of architecture, and by architecture I just mean that way of connecting neurons together, the idea of neurons at all even, that models reality quite well. So,
I mean, this is where it gets super weird, right?
All right.
Because there are many different ways you can represent information and different architectures with which you can store it, right? And like a computer, for instance, by, in default in the way we've built them, doesn't use neural networks, right? We create these neural networks in software and they get translated down to the physical circuits of the machine through many layers of abstraction, whereas our brains actually are constructed as neural networks. And a lot of the sort of performance gain in recent years has been to make the hardware of computers more closely represent what we're doing in the software. But that's a tangent we probably don't have time for. But this is where it gets weird, because it's like, well, are these neural networks like our brains? Like, is this just an example of biomimicry to some extent? Is it an example of we're just picking up a signal in the noise that doesn't actually exist? Like we're just seeing a pattern in our brains and the neural networks that isn't actually shared? Or is there something going on there? Right? Like it hasn't escaped people's attention that certain kinds of neural networks are very similar in the way they are structured to the human brain. If you abstract away from the actual physics of it, right, the chemistry and the firing of neurons and the mathematical functions, well, you get an example like convolutional neural networks or CNNs or convnets, right? And these are the kinds of neural networks that are used when processing images typically. And what makes them really cool, without going into too much detail, is that they start off very wide. So the early layers are really big. And you have a lot of these, and they just gradually get smaller and smaller, right? Thinner and thinner. So you've got fewer neurons in each layer. And the way this is done is by sort of looking at regions of the picture and then getting a sense of what's there through a mathematical operation, and then sort of compressing that into a smaller amount of information. And these are the convolutions that the name refers to. So without really going into how this works and the mathematics of it at all, we have this idea of you're identifying patterns in subsets of the image and then just encoding what kind of pattern is there. And it turns out that our brains are very likely to be doing a similar thing in terms of how we process things visually. Right? So early on, you can look at an example like, okay, well, you've just got lines for edges, right? So you might be looking and you see a page in front of you from a book. Right now, if you just look at the edges of that, well, what have you got? You've got some horizontal lines and some vertical lines and maybe some other lines on the page, whatever. But essentially now, you don't need to have all of the pixel values anymore. Now you can just encode sort of, okay, there's a horizontal line here or a vertical line. So now you just need to have like, okay, 0 for horizontal and 1 for vertical, right? So obviously it's a bit more complex than that because you can have different kinds of lines at different angles. But, you know, just as a simple example, you can see how you can compress some information through this representation. And this works particularly well in the physical world. It doesn't work on random noise, but for things that are in the physical world that have edges and are built up of regular patterns and textures, most importantly, it works incredibly well. And our brains do a very similar thing. Your early visual system from the photons that hit your optical nerve and then begin to be processed by your brain, those early neurons are identifying things like edges. And then the next set are identifying general shapes, and then the next set is identifying kind of larger patterns, and then the next one's identifying texture, and this builds up until we have an object representation in our minds, right? And this coincidence, seemingly, this similarity has not escaped people's attention, right? It's probably even a case of there was a bit of back and forth in terms of the neuroscience and the machine learning and helping each other have ideas about how the other might be working. But like, why is there this coincidence?
Again, if I'm going to distill your question there, it's really this question of why in this universe with these laws of physics are these alternating layers of linear functions with these nonlinear activation functions doing a good job of understanding anything. And as you say, right, there's this back and forth conversation between neuroscience and computer science or machine learning engineers as to how the architectures look. And I mean, it's important, I think, that we say it out at sort of, not at the outset, but it's important that we say that actual neurons and the neurons in artificial neural networks are quite different, right? They try and capture some of the same properties, but there's some properties of real biological neurons that you just don't transfer over. There's some simplifying assumptions that we make, which both help us compute these things easier.
But they're very different from a table of data. Like,
yes.
A neural network is very separate from a matrix or a spreadsheet or a search tree or something like that, right? Like they are fundamentally different structures and a conceptual knowledge representation perspective. And that is the point that everyone is sort of catching on to.
Yeah. So, I mean, what it makes me wonder, is, are there other ways of creating a brain, so to speak? So clearly, we know by virtue of our own experience that evolution landed us here, and whatever it did, it created a way to be conscious, right? A way that we could exist and be alive and have these fairly complex brains. But if we started evolution over again and it found its way to a different optimization function, what would it look like? It boggles the mind to even try and ask the question, what would a different kind of brain look like?
Yeah. But I mean, this also raises the concern or the objection that many people tend to have when I hear topics along this line, which is that, okay, yes, well, our brains evolved. They were shaped by evolution, but, we've designed neural networks. Humans are very clever, and we've now gone and built these things that do this job. And so, maybe it's a bit of bio-inspired design. Maybe it's a bit of, just coincidence. But, these things just seem to have a roughly similar shape, but, they weren't evolved. They didn't emerge out of nature. We actually went and designed them. And so they're actually kind of different. But I think that is overlooking the fact that the incentives within research and academia and the world of business value performance, right? So whatever performed better was kind of being selected for, not through the kind of natural selection we used to studying in biology, where it's how much you can reproduce, but it's the kind of selection whereby the companies and the researchers that were building the most effective computer software that was most efficient and most capable of getting good results were the ones who then got funded and continued their ideas further and published their results. And so as a result, I would say there is a selective pressure on higher performing models. And if that is the case, much like our brains evolved to be accurate or effective rather at modeling the world around us, it seems that these networks would be under a similar sort of selection pressure, just through the incentives in our economic and academic systems. Like, no one sat down to design the kind of deep neural nets we have today. There were many times in the history of AI that we had neural networks and they were eventually dismissed by people because they lacked some performance. And other techniques emerged, and then deep networks came and more computing power was available. And we found, these things actually do work. We thought they didn't, but they actually work quite well with modern computers. And so, no one would have called this from the outset. No one designed this in total isolation. And I think that feedback loop was actually kind of an evolution.
So you raised some interesting points there. And I can see why you say that this in itself has been a sort of selected for outcome. An interesting idea, though, is, when you say that these ideas or these networks were forgotten until more computing resources became available, right? Just the number of computations we could do on a little piece of silicon went up. And that makes me wonder, what other ideas are out there that were maybe thrown by the wayside for other constraints, right? So, it's just like, if you think of sort of the course of human history and the number of ideas that people come up with, you can get into these fantastic situations, right? Where maybe in the late 1800s, someone comes up with the idea for, take computers, right? There's the story of Ada Lovelace and Charles Babbage, and the constraint they had some of the principles of computing, right? But their constraint was that the physical means of doing it hadn't been developed yet, right? And so this just gets into the idea of like these multiplier effects of increasing technology, where not only is better technology a good in and of itself, but as you develop better technology, you enable ideas which were previously only theoretically possible. You enable them to become actually applicably possible, and maybe
and to be evaluated from a practical standpoint.
And so maybe a great example of this that we are maybe turning the corner into is like quantum computing, right? Where this is a field where a lot of the important results, the ones that you'll read about in popular science books, are actually not feasible given the current level of the technology. But the day that we suddenly do have that level of technology, we can suddenly do much more. And that technology would enable us to also discover more properties of quantum systems, which could have its own ramifications down the line.
Yeah, absolutely. I mean, like we mentioned with the universal approximation theorem, this was known long before the modern deep learning boom, right? We've had this for decades, but no one was actually able to then go and see, okay, well, we can approximate any function, but how can we do it in an efficient way that can learn quickly and actually be applicable to business in the real world until, quite recently. And it's almost this idea of low-hanging fruit, right? Like neural networks may not, in fact, they're almost certainly not the best way to model the physical laws of the universe and to represent them and to efficiently encode and later decode them to make accurate predictions, right? They're just one of the low-hanging fruits. And as soon as you stumble upon a low-hanging fruit in a feedback system like evolution, or like the publish-perish cycle of academia, or like the bottom-line-driven incentives of business, you're just going to channel a lot of resources into that avenue. And so like once you hit that and it's incredibly effective, well, it's even less likely now that you're going to stumble upon the harder to reach things that might be slightly more effective. But that seems to be the way things have gone. And this really ties into an idea expressed by Max Tegmark in one of his talks that I feel kind of underpins this whole conversation, right? And this is that these deep neural nets, they're only efficient at approximating a certain limited set of functions, right? And it seems like a big coincidence that those are just the kind of functions that nature seems to feed us, right? So they can approximate any function, but they're only really efficient at doing it for certain limited functions. However, nature seems to be throwing those out 99% of the time, but that's not a coincidence, right? The underlying physics produce those functions and those statistical distributions. And that is why we have gradually developed the kinds of deep artificial neural networks that work well for those physical properties, right? And many of the most effective techniques, like CNNs, which we mentioned, are organized in a similar manner to our brains. But it's unlikely to be a coincidence either, because like evolution has shaped our brains to perform well within a universe bounded by these physical properties. And so this idea of both biological systems and artificial ones having converged on a similar deep neural architecture with those interwoven nonlinear activations hints at the underlying laws of our universe in a way that makes you think that if you didn't know the laws of physics, but you knew how neural networks worked and what data they modeled efficiently, you could almost work backwards to figure out the laws of physics.
I wonder what your take is on how this view of why neural nets works, how this relates to the Manifold Hypothesis, I think it's called. So briefly speaking, this is another explanation, or maybe it's almost the same. I didn't check this, but briefly speaking, the Manifold Hypothesis tries to explain why deep learning works so well, right? By imagining, so you have this really high dimensional space that the things you're trying to classify, the images in this example, could be in, right? But you just imagine, right? Let's take a simple example here. Imagine that the set of all the things that you were classifying existed in a 3D space, right? Like a cube. Now, 3D space means that you'd have to learn where each thing is located on an X, a Y, and a Z coordinate, right? But if it just so happened that every single point of interest fell on a straight line, right, that pointed in some arbitrary direction, right? In this example, this would mean that like cats are only located along some line in that space that represents cats. Well, then you can drop the extra 2 dimensions in some sense, right? You only need to know about that line in this high dimensional space. And I believe that goes by the name of the Manifold Hypothesis. And it seems intuitively, at least, that it's sort of roughly saying a very similar thing to Tegmark's argument.
Yeah, that's a good example. I think for anyone just quickly who's struggling to visualize the Manifold Hypothesis as it's presented typically more mathematically, there are 2 good analogies you can use, right? One is to imagine a piece of paper with marks all over it that you care about, right? So imagine like a 2D plot or graph of some stuff that's going on. Now imagine you scrumple that up into a 3D ball or scrumpling of like a scrunched up piece of paper that you're about to shoot for the bin while the teacher's back is turned. And imagine that sits in 3D space, right? But all the information and the relationships you care about are captured by the 2D space of the page of that graph that you originally drew, right? So it's really just like we've got these things represented in 3D space, but the information and the relationships are only important in 2D space. And so it's like you want to reduce the one to the other. Or another way to think about it is if you think about the surface of the Earth, right? It's a 3D space, right? We're on a globe, despite what some small fraction of the world secretly believes, or not so secretly.
We do not talk about
but we actually do. We actually do live on a globe.
Yes.
But you can represent your position on the globe using only 2 values, right? Your x and y coordinates, or your longitude and latitude, right? As people are familiar with from basic geography, right? So it's like, well, we're in 3D space, so you should have 3 values to represent your position. But because we're just on the surface of the Earth, like only the latitude and longitude are needed to uniquely identify where you are, right? So that's another example of a manifold, right? So the Earth in that case is the manifold.
That's a great one.
Yeah. So I came across that the other day because I always went for the paper scrunching one, but I came across the latitude, longitude, face of the Earth one, and I really like that, and it really made it much more concrete in my mind. But this idea of the manifold, I think, is like almost isomorphic to an example that Tegmark himself actually presents, which is probably more familiar for people who are comfortable in the basics of data structures. But I think most people should be able to grasp. And it's just that if you have something like a sequence of items, so it could be a sequence of words in natural language, so like English or French. It could be a sequence of musical notes. It could be a genetic sequence, right? You have this property whereby the association between things in the future and the past is much harder to ascertain the further apart 2 things are on that sequence, right? So predicting things like far into the future, you require a lot more information about the present to be able to make accurate predictions about the future of these sequences. Like if I know what your genetic sequence is at some point, it becomes harder and harder for me to predict the further away from that point you go. The same is true for any piece of music or for any piece of text. But if you imagine that these things aren't just linear, if you imagine that they're actually like represented by some other hidden dimensions, right? So instead of a sequence or an array or a vector, imagine a tree instead. Right now, people who are familiar with data structures and with the efficiency of those data structures know that you can find an item in a shuffled binary tree in order log n time, right? That means that if you have n things, it takes you a logarithmic quantity of that to find anything. But in a sequence, in an array or vector, just a straight line of things, it would take you n times. So if you have 10 things, it takes you 10 searches to find it. But in a binary tree, it's only going to take you 3, like rounding up. So it's this idea that now imagine that you lose some information, or information is obscure to you, or it's in the future and you don't have access to it yet. Which of those 2 representations encodes the information better? Like imagine I removed half of your nodes in your binary tree versus imagine I removed half of the things in your original sequence. Like which one has the kind of structure that allows you to better guess what the missing ones were? Well, it's the binary tree, right? It's more efficiently encoding the information. This and the manifold hypothesis all seem to be related to that same idea of we get cheap neural networks right? Very few parameters are required to describe a much larger output and input space.
Well, I mean, it's interesting what you say there, right? Because, so let's say you're predicting something far in the future. I think, like, naively, right, you could look at some phenomenon and say, well, if you want to predict something in the future, you want as much data as possible. And yet it's a sort of truism that in a lot of machine learning, like a very nice and easy simplifying assumption that is made is that events are only related to the event before them or the event after them. Like that's not always the case, but it's a very nice simplifying assumption to, if I want to know the weather tomorrow, we just say, well, that's just determined by the weather today. Now we know that that's probably not true, right? But over long enough distances, that kind of assumption does hold true. And we can make those kinds of simplifications and achieve a reasonable degree of accuracy. And I think to keep with our theme, one of the reasons that is in some sense true is, again, going back to this idea of the functions that determine the laws of physics, right? The way that these functions are constructed, if you look at that function and you want to step forward in time, right? So let's say you've got the state of the universe now. You want to step forward in time a little bit and ask, what will the state of things be? It turns out when you set up the equation, that equation depends only on that initial state you found yourself in. So if you want to find where you are at time t+1, well, the equation that tells you that has only got t in it. So for me, that I'm drawing that relation there where we're saying for that whole thing, we're dropping everything at t-1 and t-2. We don't need any of that. We just need t and we can get t+1. And that's either completely trivial and you're rolling your eyes right now, or it's this really interesting property where things almost conserve all the previous information almost that got them to that state, and it's all captured in their current state. And then if you know that, then you know what it will look like in the next state.
Like how many bacteria there are going to be in a petri dish. Right? Like if you just know the rate at which they multiply and you know how much time and you know how many you started with, you can work out how many they're going to be at any point in future.
That's a possible way to think about it. And
whereas if I start with the word hello, your ability to predict what word I say in 10,000 words time is virtually zero.
True.
So that's like a Markov process, right? Like you need to know the current piece of information to predict the next piece of information. Like if I know the word you've just said, I can quite accurately predict the next word. And if I know some more about the past words, I can more accurately predict the next word. But some systems just don't need that at all. And that seems to be very much the case in the natural world.
So almost, I guess what we're saying is that, when you throw a ball up, you can just look at it at any point, and as long as you know its position and its velocity or the force acting on it, right? You can see where it goes next. You don't need to know where it was before that, right? But that's not true for language, right? And that's not only because you can't assign a velocity and a position to words, although maybe that's an interesting question to ask. Maybe there's like some analogous construct, because then that would give us a lot of useful information. But as you say, right, when we want to interpret language, even the current state of the art of language, which I'm just going to call human beings, human beings still need some context, right? I mean, as you say, when you say the word hello, I can make some reasonable guesses as to where you're going to go next. And the more words you say, the closer that my guesses would converge with reality. But we do rely on the previous state, and we rely on more information coming in, which is not the same thing as the laws of physics and how those are almost completely determined from any starting state.
Well, yes and no.
Okay.
Right? So you're right about those physical laws, but look at something like natural language, right? Here's where it gets weird. I can be quite certain that no one else in the history of the world has strung together 10 random words, right? Like if I just start thinking of really obscure things, almost as though I'm making up a strong password, right? Ironing board, cactus, antelope, serendipity, orange putrid vomit slime octopus polynomial. Right? Now those seem like totally random arbitrary words, and I can be quite certain that no one's ever strung them together in that sequence before in human history, right? There's just so many words, and you can just string them together, and every time you do, you have that combinatorial explosion of, for all possible words, you could have the word in the first position multiplied by the one in the second and the third, and it just gets huge, and so you can be quite confident in that assertion. But here's the thing. Where did those words come from? Like, I don't have some ticker tape stream of words in my body that you're just trying to predict that just come out of my mouth in some order. Like, it's influenced by my environment, and it's stored and processed in this neural architecture of my brain. Right? And this comes back to that idea of Tegmarks, where you can represent the linear sequence with a higher dimensional structure. Right? It's like the words that are coming out my mouth are determined by the neurons firing in my brain that is influenced by the sensory input from the physical world around me that is governed by these strong physical laws. Right? So there's all that's really happening is there's some convolution, some transformation happening between this multi-dimensional, highly structured input and the sequential compressed output that is the stream of actual words I'm saying. And this is presumably the reason why it's very hard for something like your spelling predictor on your phone to predict a reasonable stream of words that you would say just based on some initial starting condition. It's pretty good at predicting the next word. Like if you were like how, it will suggest R. And then after you type R, it will suggest you. And how are you? Great. So like from any word, there's some statistical correlation between the words, and you can just take the highest one, and that's most likely the word that's going to come next. But that falls away very quickly, right? But if you now go and take a whole bunch of text from the internet and a nice big computer with a deep neural network, and you shove it all in there, you get GPT-2, which was recently released by OpenAI, and which can take 40 gigabytes of training data of text, of human natural language text, and a neural structure can make something that seems to be incredibly good at predicting which word should come after another word. Right? It's eerily good at doing this, to the point that it can fool humans into thinking it is human. Right? And this touches back on this idea that like everything that is in our physical world is seemingly governed by some set of physical laws, and those physical laws are really well modeled by deep neural networks, such as our brain, and such as the artificial ones that we're employing in all machine learning now.
Yeah, I mean, that seems to be the point we keep coming back to. But
like there is no escaping that things are somehow linked. And I'm aware of how woo that sounds. And before I go light my incense and align my chakras, it's important to note that my chakras obey the laws of physics, and so does the incense, and so does everything I'm saying.
Yeah, I mean, it sounded to me almost like the direction you were going to go in, right? When you were mentioning how, so yes, on some level, I can point at speech and say, look, it doesn't seem to follow this very nice pattern of if you give the previous word, what the next one will be with perfect accuracy, which is true of, let's say, the case of throwing a ball in the air, right? But it sounded to me like where you were going with that is the structures that are forming that speech, right? The language model in your head, the neurons firing, those things are made out of atoms, and those atoms obey those physical laws. And so, in some sense, the words are an abstraction, or I'm not even sure how to think of it. Are they a derivation or an abstraction? But they're in some sense abstracted away from these very simple particle update laws, if you want to call it that, right? Laws which update the position and momentum of all these particles that make up your neurons. And yet, from these very simple laws, you get this very high dimensional, difficult to perfectly pin down data structures, which is human speech. So yeah, I don't even have a good way of thinking about that, but that sounded like the direction it was taking.
Well, think about what else you would do, right? If you're this being that's developing a mind and you want to start communicating with other beings, conveying parameter sets that are in your neural network to their neural network that has a slightly different structure to yours, right? You have to translate it into some exchange medium, into some standard. And language seems to me to just be the sequential sort of byte string that serves to do that, right? In the same way that when I have, a good piece of software on my computer that's running Mac OS and I want to give it to you on your machine that's running Windows or some really cool Linux distro, on totally different hardware, I have to translate that, into some data file that's just a linear sequence, and then your computer's going to unpack that and then do a whole bunch of work to conform that back into the right structure to fit your brain, your model, your architecture, right? So it's like we've got this vocal tract and we've got these hands that can produce things in very limited low dimensions, and so we have to translate these high dimensional structures of our ideas into lower dimensions to exchange them and then build them back up again in another mind or another piece of hardware.
Yeah, I mean, that's a really trippy idea when you put it like that. The idea that what we're doing when we convey ideas, when we speak to people, when we use language, when we, to use maybe a sort of very Richard Dawkins idea here, when we spread a meme, is we are in some sense trying to train other neural networks that we find ourselves living amongst or amidst. That's a very depersonalizing way to view it. But I mean, this is also the source of, so lest we sound dystopian here, this is also the source of all the joy that you experience when you're with someone that you love, for example, is the fact that you've allowed some internal state in their head to be communicated over to you via several different mediums of communication. And that has retrained your neural network, if we're going to speak of it like that, and updated the weights and the parameters in such a way that you can now experience that positive emotion.
We just aren't yet consciously privy to the exact function that is doing that. And the function is going to be different in every brain, right? Whereas we are privy to the standard representation of the law governing where the ball that you throw into the air is going to fall. But if you were, raised in a dark room and given no access to the outside world, and you weren't allowed to move around and play with things and develop an intuition for physics, and then I took you outside and threw a ball into the air, you'd have no idea what was going to happen next, right? But as soon as you start having access to the information of, oh, this is how things obey, like these are the laws that things obey, like I can write down the kinematic equations that model how physical objects are going to move at the human scale on Earth. And then I'm able to make these predictions, right? But we don't have those functions accessible to us for things like language, for things like music, for things like love. But we have some approximators for those functions. And we do a pretty good job at approximating things. And increasingly, our hardware is doing a good job at approximating things.
Yeah. I can sort of just imagine that speaking like this can feel to people like you are taking a very deterministic or very reductionist approach to human lives. And I know that can feel to people almost uncanny. You get into this uncanny valley where you're experiencing things, and yet when you try and do some sense making, you try and understand why the thoughts that you're currently thinking are there, where they even came from in the first place, and you find yourself in a strange place where your reasons really start to be a bit of a regress, right? And you can eventually point at physics, right? You can point at the very deterministic idea of it, but it still feels unsatisfactory, right? Because we want to point at causes and we want to point at free will stories.
Yeah. Well, because our our biological neural networks have been trained to operate efficiently on those conceptual representations, perhaps. Whereas conceptual representation of mathematics or however we are choosing to express this, and the language we're using to communicate about it is not what it was inherently designed for.
Yeah, a lot to think about in this conversation.
And I think we should still just point out the fact that this doesn't mean that everything obeys the laws of physics in a conceptual sense, and that we can now just throw out all the theory about informational entropy or about Markov processes or about anything like that, right? Like a game of chess exists in an abstract plane, right? Like the physical board is in our physical universe, but the concept of chess exists in the same realm as any of the ideas in abstract mathematics. And so the game of chess is still computationally hard. It doesn't follow the laws of physics, right? Like a physical battle or a soccer match or something like that does. And so you can model things like that using these deep and cheap shortcuts that exploit the relatively simple laws of physics. But things in a much more abstract sense are still hard problems. And as a result, it is still hard to solve them.
Yeah, that's an interesting point you bring up, actually, that, we can create ideas in some sense, right? And those ideas are not beholden to physics, as in the rules that govern them are not the same ones, right? I mean, you can just do this trivially. You just say, well, I'm imagining a universe and the laws of physics are different. And there we go. And I guess what we're saying is you could do that in such a way that the machine learning architectures that work really well in our universe with our laws of physics would not work really well in that universe. But now,
on the same problems, yeah.
But now that makes me wonder, right? So, I mean, we're seeing, at least in some games that I guess, never mind, this probably does make sense, right? So we're seeing AI and machine learning techniques start to get like really good results on video games, and those video games tend to be built on a physics engine, and that physics engine tends to mimic, or at least come close to, the physics of the real world, right? I mean, the game designer might change the value of gravity because in that game they want people to jump really high, for example.
Yeah, but you're just changing a single parameter there. It's easy to adjust.
So I guess what we can say from that, though, is, I mean, the fact that these systems are seeming to learn fairly well in domains that are not directly beholden to the laws of physics, right? We can somewhat alter them. Maybe that also, in some sense, indicates a little bit of robustness of these models to like similar laws of physics to our own.
Yeah. Well, I mean, to be fair, the physics aspect of the games is not what the algorithms struggle to beat the humans at. A large part of designing these systems that can play against humans is actually limiting how much they can exploit their inherent advantage in speed and reaction time and being able to accurately predict where things are going to be. The challenges with these games are largely around the strategy. And that's why it tends to be games like Dota that are the challenge for machines. Because it's the strategy aspect of it, not the actual physical aspect of it. Like if you try to play a machine at FIFA, it would destroy you, right? Just because like it can just have perfect timing, and as a result, it will always just be better than you. But when you get to the strategy aspect of these intensely strategic games, StarCraft is being another example, then that's where planning and these sort of other higher order approaches are super important, and the machines are not yet that good at it. But coming back to chess, right? We just said that at the beginning of the podcast that these artificial neural networks, years ago already were defeating the best humans at chess. And it's like, well, we've cracked chess. But yet I just then said that chess exists in an abstract sort of mathematical realm that could exist in another universe with different laws of physics, and it's not actually beholden to those laws of physics. So it's like, well, I've just said two contradictory things there.
It seems like it almost.
When we said we've cracked chess, what we meant is we just were able to beat the best human at chess. Right, we're not scoring our performance at chess the same way we score our performance at predicting cats versus dogs, right? When we say we've cracked a game, we just mean we've beat the best human at that game. We're not achieving 100% at chess, whatever that would mean, right? Like it's possible that we humans only ever, even the greatest chess players of all human history only ever achieve like 1% on the chess goodness scoring function that I'm hypothesizing here. Right, so it might be possible to get to 100 on that, but all we do is we just get to beating humans. And if you look at how these things learn from historical games, what we did is not model the game of chess. We modeled the neural patterns of how humans play chess and beat them at that game, not at the game of chess.
That's an interesting point. I keep wondering though, again, so chess is this idea, abstract as it may be, that came from human minds in a universe like ours, beholden to our laws of physics. So I'm just trying to think if I can conceive of a chess that's independent of that, and this is probably more just a limitation of my neurology than it is of the actual concept here. But
yeah, like sure, the influences are there in the manifestation of it. But the core, like if you just reduce chess to a mathematical model, that could exist outside of the laws of physics. It does. Right, and that's why things like chess and Go are so combinatorially expensive to search through. That's why you have to come up with these other approaches, because they just explode on you, much like the images would explode if they were all just random noise. But now we've just sort of wrapped it in this layer of, okay, we're going to use these pieces and move them on this 2D board and put them in blocks. But the underlying mathematical structure that you would use to represent chess is not beholden to the laws of physics. Right, it just happens to be that the way we play chess is very much grounded in our neurology and psychology, and it seems that is where the algorithms and the artificial neural networks are actually beating us. Is they've just modeled how humans think about chess and play chess, and why we decide to make certain moves that aren't necessarily entirely grounded in the raw mathematics of it. Like it's a much more limited search space. Right? Like we inherently can't think of all the ways we might play chess in a way that a human can't think to play chess. So, the best human chess player can only play chess in the ways that a human brain can process the game of chess. So a neural network only has to be as good as the best human or better. But it's just learned from every human game that's ever been played, and so it's really good at the way humans play chess. But that doesn't mean it would beat some alien from another universe at the same mathematical representation.
Okay, I'm hearing that. I'm inclined to sort of wind this conversation down here. I'm not sure if there's more points you want to touch on before we leave off.
No, I think we've really gone into depth here.
Yeah,
both in subject matter and in execution. But yeah, I think maybe just to tie up some loose ends and conclude briefly would be a nice idea. Really just to emphasize this point that it seems when you stop and think about it that these deep neural networks are pulling some kind of swindle, as Max Tegmark puts it, in that they are unreasonably effective for the kinds of problems they're solving. But looking at it from another perspective and looking at the underlying physical laws of our universe and how that influences the data that these models represent, it seems that the connectedness between neural networks, be they artificial or biological, and the laws of physics governing the world we live in is inextricable. And leveraging that as best we can seems to be a good approach to enhancing the performance of these systems further, as well as understanding our own brains, as well as understanding the laws of physics better.
Oh, that's awesome. I think it's a good summary. So,
yeah.
On my side, I think maybe to wind us down more gradually here, I was thinking it would be cool to get just one recommendation each of a smaller or lesser known podcast that you are enjoying at the moment. So, I mean, you're not going to sit down and suggest the Joe Rogan Experience, because there's no way that someone is listening to this that has not heard of Joe Rogan, for example. Or maybe there is. I don't know.
Unless
People are strange.
Unless it's our mom.
Unless it's mom. Thanks, mom. So, yeah, any suggestion on that front to wind us down for the evening?
Right, so yeah, a classic that I've been listening to for quite some time now is the MIT Artificial Intelligence podcast with Lex Friedman. So it's Frid. as he says in every single episode, which is fair because it's not a common way of spelling the name. So I think he grew up in the Soviet Union, if I'm not mistaken, and he also does Brazilian Jiu-Jitsu, as well as being a professor at MIT working on machine learning and AI, especially with regard to autonomous vehicles. So very closely related with Tesla and Elon Musk's work. And he's collaborated with him many times and actually had him on the podcast a few. But a fantastic podcast. He publishes stuff all the time, and it is with some of the greatest minds in artificial intelligence, machine learning. You know, everyone from your sort of your classic heroes of the discipline, like your Stuart Russells, to the more popular young guns like your Ian Goodfellows, and but yeah, it's just a really thoroughly good set of quite technical conversations between brilliant minds and very influential figures and knowledgeable people in the field of artificial intelligence and machine learning. And if anything we said in this podcast relating to the machine learning and deep learning side of things tickled your fancy, or if you're inclined that way whatsoever, it's definitely one of the podcasts you should listen to. The return on investment is intense.
Yeah, that's great. I can second that recommendation. It is a really great podcast. I think on my side, a podcast that I've been getting into a bit more recently is called The Scientific Odyssey. I think the host is called Chad Davies. And it's sort of a podcast about the history of science and how we develop knowledge. So he has like a series on the different theories of the atom, you know, different theories of, let me say it talks you through the scientific method and the inventions that were necessary to advance our knowledge. And so while a lot of the podcast has focused on ideas that are actually outdated now, it's still a really great journey that shows you just how far we've come. And in some way, I think is inspiring to how we might have so much further to go. So yeah, I've really been enjoying that recently.
Fantastic. Cool. Definitely worth checking out. But I think that brings us to a close. We've been through some pretty intense loops here and tie-ins between different topics, everything from data structures to neural networks in the artificial and biological sense, to some very metaphysical discussions about the nature of reality, the physical laws underpinning it, the separation between the abstract world of mathematics and the concrete world of physics and the universe we live in, and how that all connects to the almost unreasonable efficacy and efficiency of our modern deep learning neural networks. And I think the takeaway from my side is now to go and learn some more physics, train my biological neural net on the laws of physics, because they seem to be the cheat codes to the universe.
Well, I need to go learn some more deep learning. So with that, I will leave that there, sir. Thank you very much.
Until next time.
Great. Cheers.
Thanks for listening to the Bit of a Tangent podcast. If you enjoyed this episode, please get in touch with us and share your thoughts. You can email us at podtangent@gmail.com or connect with us on Twitter through the handle @podtangent. For more information about us, our backgrounds, and other projects we're involved in, visit our website at podtangent.com. That's podtangent.com. The best ways to support us are to share one of our episodes with someone who may enjoy them, and to give us a rating or review on iTunes. That way, Apple knows that we're actually worth listening to, and all the platforms that pull content from them will too. We both love having these discussions and relish the opportunity to share ideas with like-minded people around the world. So your support and listenership are sincerely appreciated. Until next time.